the second term already on 11th February, so we still have some time. So maybe we'll talk about formal issues already next week. And today let's focus on the lectures that we have left, unless you have some important questions and it's not requiring instantaneous answer. If not, let's go. So we began last week power reduction in embedded systems, and I tried to prove you that the major problems in case of power dissipation in CMOS circuits can be split into two categories, so dynamic and static, and those two categories then we can split into two subcategories each. So the power lost during switching, the power lost because of the imperfections in CMOS circuits, so the so-called short circuit, the static current, the bias current, or the power supply current, and the power loss here, and the last one, the leakage itself. So a couple of elements here. So the dynamic power, so the switching and the static, and for the switching and short circuit, of course, not the static, but the short circuit, and static is the power supply or the bias current, and the leakage itself. In case of the switching, so small explanations for the switching and short circuit. By switching, we talked about it last time. So the major, so we need to charge the gates of the next stages. But in case of this, so that's about the switching itself. The short circuit is the second arrow. So this is the arrow showing the problem. So we have the CMOS circuitry, which means that there is a P-tape and N-tape MOS. Of course, it should be only one transistor on at the same time, but because of, for example, this parasite capacitance, we have a phenomena that there are current spikes flowing directly from VDD to ground, because we have, because of imperfections, because of the capacitance of the gate itself, and of limited non-zero impedance of the serial of the driving source. So the impedance here, so that we have a driving source and the resistance and the internal resistance here. So if this is non-zero, and it isn't, and because of this fact, these elements, there are short moments when the VDDs, the current is flowing directly to the ground, heating up this transistor, of course, and this transistor, and of course, being a parasite effect, the effect that we want to avoid. And as well, in case of the dynamic power, switching power consumption, in case of digital systems, it's directly proportional to the frequency and the capacitance of the load, but also proportional to the square of the power supply voltage. Therefore, every reduction in supply voltage, in the value of the supply voltage, is required when in the circuits where we want to reduce the power consumption. Okay. Starting part, it is a bias current for analog circuits, the low power time-keeping oscillators. Let me switch off the camera because I get the message about problems with internet again. Okay, maybe now I will hearable and before the camera. Okay, and the leakage current itself coming from some imperfections, from some finite resist impedances of pins, of inputs, of transistors, and that's the place, as far as I remember, finished last time. We were to begin from the answering the question whether static power is a problem. Because there is a huge difference in the values normally. In case of active, so active or dynamic, maybe not active, but the dynamic part consumption normally, we talk about currents from 10 to 100 milliamps at the power supply voltage 2 to, let's say, 3.3 volts. So that's something that we usually have in case of microcontrollers and around. In case of static power consumption, we talk about usually 1 to 100 microamps only, of course at the same voltage, because it's natural, the power supply is the same. So as you can see, that the difference is 3 orders of magnitude between static and dynamic factors, and dynamic and expected power losses because of the static factors and because of the dynamic one. In digital circuits, it's more or less something like this. So when the static is important compared to dynamic, the dynamic we need to especially focus in if we construct a device that is running 100% of the time, or majority of the time it's running at full throttle, while the static power consumption is naturally important if we talk about battery-based systems. So the systems which are to be very frugal in case of battery consumption, in case of power consumption, so that we need to squeeze the most out of a tiny battery. That's why the static power consumption has to be analyzed with precision, and with caution. Yeah, the problem with the static power consumption mainly depends on 2 factors in case of CMOS circuits, at least. So it's about gate leakage, which means that in CMOS we've got the oxide here, the oxide which is showing very high impedance, but of course it's the impedance is not infinite, and because of this we have some leakage here, and as well the second sub-threshold leakage, which means that even if there is no channel still between source and drain, there is some finite resistance or finite impedance, and all this goes into picoamps or nanoamps. But again, we talk here about hundreds of thousands of transistors, if not millions today, even in microcontrollers, which means that if we multiply picoamps by hundreds of thousands, then we'll end up with those microamps pretty easily. Naturally, because of this, here we talk about gate leakage, depending on the gate impedance. So the smaller the gate, the smaller the distance here, usually it's worse, and that's actually happening. So if the technology technology node goes down, then usually the leakage power increases. So here is the normalized, of course, leakage power, because think about the difference in scale, that the dynamic power is a few orders of magnitude, 2-3 orders of magnitude higher than the leakage power or the static power normally. Yet the dynamic power, of course, is going down because we have lower capacitances, for example, and lower voltages, main of all, because the higher technology node, the lower core voltage. Anyway, this chart, so this table is showing that it's not all that rosy to have the technology node reduced, and in some cases it's better to get to use in a design older technology device, so the device that is produced in older technology node, because it will have lower leakage power, but that's only for very low power devices normally, because this is dominating definitely the dynamic power consumption, the total budget. So normally we like very much to have better technology node, lower technology node, or newer technology node, so to be able to get low, to be closer here, so to have reduced dynamic power part, even if this would cost us a few microamps or microwatts more on the static side. In case of, maybe we'll skip this. How to get the best performance out of a tiny battery? The subject in general I would say this way, this subject, the simplest answer, although maybe not very very brilliant, I would say, is to get some experience in the subject. So get experience in the subject. So generally, it's something like with RF design in electronics. So the major so we will so we need to, as a developers, we need to just design a couple of such circuits and see the problems and see the possible improvements. So that's the simplest, yet as I mentioned, not the first, not the best answer, because not so to get experience, how to get experience. And yet I would like just to show you at least where to start with in case of battery, low battery design, and what to focus on as the main subject, as the main elements. Although these are not all elements that we need to take care of if we want to design really low power device, because at a certain level of low power, really everything matters. Everything starts to matter, even the shape of the PCB board. It's exactly, from my experience, it's a very analogous to the design of radio frequencies, where everything matters really. And same is here. So the subject is not really that simple. A couple of elements to prove this, I would say, just a couple of factors influencing that I would like to show you. They are, I mentioned, as critical aspects, but in case of low power design, everything is actually critical. So if we get down to nanoamps or microwatts, then really everything gets critical. So for example, I would like to show you the influence of the wake up time of a microcontroller at low power performance, the oscillator speed choice, the choice of instruction set architecture, even the peripherals matters. So what kind of peripherals we choose in our design. So is it better to use the, for example, parallel connection, or SPI, or I2C, or ADC, certain type? This also matters at certain level very much. The temperature of operation has some influence as well, and for example, the existence of certain low power features in a microcontroller, which is as the heart of our embedded system. So to start with, the wake up time. Why is it critical? So we need, naturally, the wake up time has a sense and has any meaning if we talk about embedded systems that are used periodically. So not all the time, but the systems that are to be switched on, for example, every 100 milliseconds, or every 1 day, or every week. So we need, of course, if we talk about systems that need to be woken up every week, then you say, so wake up time is the problem. This is every week. But the question is not about how often actually the system is to be woken up, but what's the ratio between the wake up time and the operating time. So even if we wake up the system every week, if the system is to be woken up every week, then it is to make a measurement for 1 millisecond. Then having an oscillator with a startup time of 100 or even more, 100 plus millisecond, you must admit that it has absolutely no sense. And so 1 millisecond to 100 millisecond startup time. So here it is. For this reason, it does have a time. Naturally, if we talk about, it's an extreme example of having a system woken up every week, but normally we talk about operating systems, I don't know, woken up every second, or really 10 times per second. And if this is 10 times per second, the system is to work for 10 or 20 milliseconds during it after each woke up. Then again, we must really think twice when using this kind of combination. So generally the phase look. So the phase lock loop usually needs some time. And in these conditions, we should choose, and that's usually the preferable choice in this kind of circuit. So the internal RC oscillator. So here it is written fast because usually the RC oscillators are really the fastest one to start. And the fastest here is an example from some microcontroller. So not always there is such a huge difference, but usually there is a significant difference between the startup time of a RC oscillator against the crystal or against the PLL. So the PLL is usually the slowest choice. Yet the internal RC oscillator, you should remember we love them very much for the very low price and for the ease of use because they are very simple. We like them very much, but we don't like them for two reasons, for two factors. We don't like the internal. Also, maybe the question too. So for you to wake you up, why don't we like the internal RC oscillators? So what's wrong about them? So there is plenty of good, but what's wrong about the internal RC oscillators? Two major elements. What's wrong here? Who remembers?
So low stability for such wake-ups times?
Yes, exactly. That's one problem. Problem number two. Anybody?
Maybe temperature stability?
Yeah, it's about low stability. It's limited frequency. Limited frequency from practical point of view. Sorry about this. From practical point of view, the problem with the internal RC oscillators, and that's the second factor why we don't like it. Usually, in many applications, this is the true deal breaker. Because the low stability, if we don't talk about if we don't intend to use USB or UART or CAN, then actually this low stability is not such a problem, or if we don't want to make a route and clocking. So the low stability is usually not such an issue, but very often the major issue is the limited frequency, frequency range, because in case of internal RC oscillator, RC oscillators, the range is quite often limited to something like about 16 megahertz. So it's between 8 and 16. It's okay for AVRs. It's okay for microchips. Yeah, not really for microchips. Already not, because they need much higher frequencies, and it's definitely not good for 32-bit constructions. Well, we would like to have 200 megahertz or something like this. So, of course, this would be the preferable choice because of the startup time, but because of those problems, those the most important ones that you have written at the top of the page. Sometimes we need to design our circuits to use either this option or this. So either of those slower options. But as you can see, the wake-up time sometimes may matter. Then the second thing, interesting one, is the oscillator speed choice. So is it better in general, would it be better to process shorter at higher clock rate or slower at lower clock rate? Because lower clock rate means smaller current consumption. So here we have an example of the active mode current, and at the 1 megahertz, the current is, I don't know, it's about 0.4 milliamps, let's say. And at 16 megahertz, the current is about 4.5 milliamps, something like this. So it should be around 16 times. So it's not exactly this, but it should be about 16. The difference between those two values should be around 16 times, which means that this will be lower than 0.4. Because in case of microcontrollers, usually there is a very close to linear dependence between the frequency and, here you can see this chart. This is showing linear dependence between the frequency of the clocking and the active mode operation. It does mean that if this is linear, it does mean that theoretically there is no difference. So if you process at for 1 millisecond some data at 16 megahertz or for 16 milliseconds at 1 megahertz, theoretically it's completely the same current consumption, so total current consumption. So in case of microcontrollers, it's not really so important from this point of view to decide to scale down the clock frequency. In case because if we put microcontroller to sleep and we woke it up, then usually, and to do the job and then put it back to sleep again, then usually the highest clock frequency is the best. So usually it's the best, although usually it's the best, but at some situations it may happen. So in more advanced designs, might be useful to scale down the frequency a bit, or to some value, maybe not down to the lowest one, but to be somewhere on this chart, not really at the top, but somewhere. But it's from my experience, it's quite rare. Usually full throttle and then back to sleep works pretty well. What's the problem with the with choosing the small remark with being here or here, with choosing the frequency, that sometimes may be a decisive factor. The difference is, take a look about, and that's quite standard in case of microcontrollers, let me wipe it a bit, is that if you want the highest clock frequency, then you must supply a microcontroller that it's, in this case, from 3.3 to 3.9, or now it's not even 9, it's here it's about 3.7. This is the usable voltage range. If you have lower voltage, if you designed a lower power supply at your board, available at your board, like 2 volts, then take a look. In this microcontroller at 2 volts, you are allowed to clock it at 1 megahertz, but definitely you are not allowed to clock it at 16, 12, or 8 megahertz. So sometimes choosing the highest clock frequency has to be viewed with the respect of the supply voltage that we have on our board and that we are using on our board. So also have this in mind. So the oscillator speed choice is not usually that difficult, but be careful about the supply voltage, I would say. Another factor influencing naturally the power consumption is the instruction set architecture. The instruction set architecture, which means that how effectively our algorithm will be processed on the particular architecture. So an algorithm or a program or a code, how effectively it will be run on the architecture. And this is in fact really difficult. So this is the analysis of this is really difficult, and depends on a great amount of factors. Really great amount of factors. I try to make just to give you an idea how unpleasant this is. Theoretically, I try to compare a few architectures. So the very tiny PIC-10 F200 clocked at just 4 megahertz, so 1 MIPS processor, slightly larger but still tiny PIC-12. Clocked at 20 megahertz, medium-sized PIC-18, some version of at 40 megahertz, then 16-bit PIC-24, which is 16-bit, clocked at 32 megahertz, but here is 2-to-1, which means that effective clock rate, instruction clock is 16 megahertz, while here effective clock is just 10. So this is naturally much faster than the PIC-18. To this, I added the tiny ATmega, so the very basic 20 megahertz versions of Atmel. and 16-bit low power MSP 430 version F1, and this is version 5. So the low end 16-bit and the high end, if we can call it 16-bit, clocked at 25 megahertz. And for comparison, I chose a few basic instructions. Some of them are shown in the table, some of them are off the table, giving us some artificial program I prepared. And based on this, I calculated the supply current version that is necessary to deliver 1 million of operations per second for each architecture. And take a look. The tiniest one, the smallest one, PIC10, to deliver 1 million of operations per second, in fact, requires 0.157 milliamp times 2 volts, which is about, this is the lowest that you can get. So this is 0.35 watt, a milliwatt, of course, because this is in milliwatt. This is the power that we need to deliver to have 1 million of operations per second on this core, on this instruction set architecture. And much better we get at PIC12. What a surprise! So PIC12 delivers us, take a look, 0.18. So the same, we get the same. We have same processing capabilities, but at half the current, at half the power of the PIC10. PIC18 and PIC24 greater, of course, much larger values, because we talk here about 1.8 and here about 2.1, let's say, milliwatts. But at the same time, take a look, PIC24, okay, we have to spare more energy. We have to deliver more energy than on PIC18. But nominally, PIC24 is more than twice as fast. It's about 3 times faster than PIC18. So if I were to choose, I would choose definitely PIC24 over PIC18. Naturally, for low power, they are much worse than smallest PIC12. In case of AVRs, worse than PIC12, but remember, Titani is a bit larger, so a bit faster, and than PIC10 and PIC12 even. But interestingly, the 80 mega 168, which is on the level of PIC18, of course weaker than PIC24 because it's 8-bit, but it's faster because it's 20 megahertz instruction clock rate. And so we can have the same for 1/3 of the power. Take a look, 1/3, and same price, same size, same capabilities, but 1/3 of the power, just by choosing the right instruction set architecture. That's the difference. In case of the 16 bits, 0.88 here and about 2 milliwatts here. The level in case of an MSP the same, like competing, because this is 16-bit and this is 16-bit and this is 16-bit family, same level. In case of this processor, again, better than the PIC18, worse than 80 mega. Still, the value pretty decent, 0.88 per 1 MIPS of current. So take a look. Difference in the instruction set architecture really matters. And as well, not all that shines is gold, because we have the smallest one, PIC18, PIC10, which is the smallest of the smallest of the smallest, and it has comparable power consumption too. Much better, much more comfortable 80 Tiny 10. And again, if I were to choose, 80 Tiny wins clearly here, like 80 mega with PIC18 here. What is the last thing that I wanted to you to stop by for a moment is the power down current. So the static or leakage power that we need to that is consumed or required by a particular architecture. It depends mainly on the technology, but also a bit on the construction. Still, a clear winner is this PIC12 with mere 100 nanowatts. 100 nanowatts, so it's a very tiny number, but interestingly, very close to it is PIC 24, which means that statically it's designed perfectly. I would even say superbly with just 100 nanowatts, outpacing the 80 mega, for example. So PIC 24 is giving you higher processing power, 16-bit operations, and of course actively it requires more than 80 mega, but in the sleep, in power down mode, it's even better. So here, as I mentioned, pretty difficult thing choosing the proper instruction set architecture, because it's not really that simple, and the analysis is really time consuming. Besides, the analysis must consider our algorithm, so must consider what we expect from the microcontroller, or what is the application area of the microcontroller, because depending on the application areas, we are using different features. And then we come smoothly to the next element, the utilization of peripherals. So the choice of peripherals also matters, and the simplest, so not maybe losing too much time here, the simplest comparison: should we use UART, I2C, or SPI in our design, and what is better? Here you can see the current consumption of the block itself for some microcontroller, and then the time that is required to send a certain number of bytes. So here is in this example calculation 10 bytes. How much time is it required at those speeds with those interfaces to send the data? So simple analysis showing us yet how large the difference may be between interfaces, and how important the peripherals may be. So the peripheral choice may be in real life, especially when we talk about very low power operations, very low power in very low power design. So take a look. The SPI can do the same, so can be used to transfer data at 20 times, more or less 20 times lower power consumption compared to competing I2C, especially because UART is a bit different interface for a bit different areas or applications. Yet the I2C definitely competing, and I2C, as you can see, has a certain disadvantage here. From factors that sometimes are considered, although not very important, and although not important at the first estimation of power consumption, is the influence of the temperature on the power consumption. The temperature, the major element that is influenced by the temperature is the high leakage current. Here the leakage current is rising dramatically, I would say. So of course we start from nanoamps, sometimes hundreds of nanoamps. So even if it rises 10 or 15 times, we are still within microamps, sometimes even a bit below. But again, if we consider very low power circuitry, then those microamp or a few microwatts in other units matters. Therefore, the temperature, the high temperature, or the operations at high temperatures should be considered for this reason improper. Of course, sometimes we simply don't have a choice, but still, this is a feature that sometimes matters. Very rarely, but sometimes. More important in case of low power consumptions is the presence of special features in microcontrollers, special features that are helping us to control the power consumption, to monitor the power consumption, or to lower the power consumption in a microcontroller-based embedded system. What are those low power features that we expect in the microcontroller would have? And I would say that the features are pretty necessary today. And if the microcontroller is missing majority of those features, most of those features, then you simply should choose another one that includes them. So the features that I find useful, very useful, is first of all automatic wake up on time interval. So the microcontroller, it's a really must-have today. So this is really the same. So those two features, just I put two lines showing the same. So that we can put the microcontroller to sleep, and then it should be able to automatically wake up, either with the use of special timers. Usually it's a watchdog timer used for this, or real-time clocking is used for this, or that we have the possibilities to wake it up through the special external lines. So the microcontrollers without these features usually are woken up through the reset only by setting a reset button low or active. Yet this is really limited, and actually it means that only the old processors have this limited capabilities. All new ones, all new processors for the use in low power circuitry allow waking up on some intervals or some wake up timers. Then a quite important feature, and maybe not as popular, but still pretty nice and still gaining popularity, are the power domains. So the power domains in case of microcontroller, it means that the peripherals are gathered together, some peripherals in a few groups, and the groups are sometimes sharing a power supply. Sometimes the groups are sharing a clocking, and it means that we can switch off the whole group and then switch it back again, which saves time and energy, because we don't need to switch every peripheral separately. We can switch them back together at the same time, and as well we can control the clocking or power supply of those peripherals as a group, not as one by one. Then another important low power feature, which is today a must, in fact, is the retention of RAM during standby. So it does mean that we can switch off a microcontroller and switch off the peripherals, but the RAM should stay supplied. We talk about, of course, the SRAM, so the registers, in other words. The SRAM does not require too much current, so the SRAM is power efficient normally comparing to DRAM especially, but sometimes it's power efficient, but still, of course, in some constructions it's switched off completely when we put microcontroller down to sleep. But from software developers' point of view, losing registers during sleeping usually means the necessity to reset everything, which means the necessity to reinitialize everything, which means, of course, huge waste of time. That's why RAM retention sometimes is much better, especially if we have periodic wake up of a microcontroller every tens or hundreds of milliseconds. It's much better to have RAM retention feature than to miss it. So again, a feature that is well welcomed today in microcontroller. And the next one, power monitoring. Power monitoring, so that first of all, the supply voltage supervisor. So various names for it exist on the market. So depending on the technology, on the manufacturer itself. In general, the name of supply voltage supervisor is much better than brownout reset. What is a brownout? Good question. Supply voltage supervisor already tells us the problem and tells us what it does do. So that the supervisor has to be able to shut down the microcontroller. First of all, to inform a core that supply voltage is getting to dangerous values. Second of all, it is to shut down automatically the microcontroller when the supply voltage gets below this some threshold, in order to prevent malfunctioning or false operation of a microcontroller. So very important feature today in today's microcontroller systems, quite often present, but again, you can find on the market microcontrollers without the power monitoring on board. And the last the feature that's already will be described a bit more after the short break. So the existence of sleeping modes. But about the sleeping modes and what sleeping modes can we expect in a microcontroller? So what's the difference between sleeping modes? Already all about this after 10 minutes break. So let's have a 10 minutes break and we'll be back afterwards. Hello, welcome right after the break. Yeah, before we continue, a small remark about the PCBs, because we've got the PCBs came to my hands on Friday. I gave it to Julka Rzepka, and she gave most of them. She handed to proper people, but there is still 4 of you that didn't get the boards themselves. This is Grzegorz Krupa, Lin Chen, Javier Samos, and the fourth one. Let me trace back. This project was this. Generally, we can get the boards from her. She has them, so you can. There are 5 boards. There are 5 boards, so you can do whatever you want with them. Yeah, exactly. Okay, the violet one. Let me check the last one. Yeah, the last one is Mohammed. So the 4 boards. Julka has 4 boards for those that I mentioned. So contact her to grab the boards. I know, maybe to run them, but definitely to describe them. Okay, let's go. So sleeping modes. Sleeping modes. In case of microcontrollers, they have different names. But what's the basic idea about the sleeping mode? Basic idea, because in case of microcontrollers, we've got the CPU itself, which usually consumes the largest amount of energy. But also, besides the microcontroller, we can scale it up and down with clock frequency naturally, but still it's so-called active mode. Besides the microcontroller, we've got various set of peripherals, and we can generally classify the sleeping modes into 4 major categories of the sleeping modes. They have different names sometimes from manufacturer to manufacturer, but the general meaning or grouping is the same. So the first mode, active mode, is the mode where everything works. So the microcontroller, so not the microcontroller, sorry. In the active mode, the CPU works and all peripherals are working here. So this is mode active. Then if we switch off the CPU, we've got only peripherals running. Then we talk about such a mode as being an idle mode. Idle because the CPU is waiting for some action, waiting for some event to happen. And nothing, and until anything happens, it's not doing any operation. So this is really not that seldom. Not that seldom, because in some applications the microcontroller, so the core itself, is used just for configuration, and then the peripherals, when configured, are able to work alone, I would say, even to share some information. So for example, the ATX Mega, where the peripherals can share peripherals through Event Cloud. And this is then we call this mode in idle mode. So then the power consumption of the microcontroller reduces significantly. In all those cases, we've got also, I forgot about, the memory is running. So the memory is running naturally in the idle mode. Program memory is not that important. and can be switched off because we have no program to be ran because the CPU is inactive. Standby mode is the mode where only some peripherals are running. Peripherals are running. Also, the memories are running, but here only static RAMs. So the registers and all the scratchpad memory, so this kind of memory is running. As the name suggests, in the standby, only the most important peripherals that are used to wake up mainly are used to wake up the microcontroller, the CPU itself, and the other peripherals are used. So, for example, watchdog may be running, some port monitoring may be running here. So that's what we call a standby mode. Standby mode, comparing to idle, is much more efficient. Yet the capabilities are limited, but not as limited as in the backup. Backup is only the mode with some peripherals running. No memory is supplied, so no registers are supplied here, which means that the mode is quite problematic from programmers model point of view, from the software developers point of view. Yet naturally the backup mode is definitely the simplest, the most efficient out of those, and with the lowest power consumption. So normally between the modes we can change. So here is from some microcontroller, where this microcontroller having the sleepwalking mode, whatever it is. But from our perspective, really, those four categories, the most important, the active where everything is running, the idle where everything but the CPU and program memory is running, standby, very highly configurable mode with peripherals, all necessary peripherals running, and memories, necessary memories running. So majority of operation is done in this idle and standby mode. In fact, in low power circuitry, and the backup mode, everything is actually switched off, and only the very basic peripherals are left with major functionality, just to wake everything back to active operation when an event happens. And so in the idle mode, we have CPU clocks off, because that's usually what I mean by switching peripherals. Why not switching power supply? Because you are when we think about switching something off, quite natural it seems to switch the power supply off and not the clock. But in microcontrollers, especially in the idle and standby mode, we don't have power supply switched off, but we have usually switched off only the clocking. The reason is to be able to wake up faster, because of the capacitors that are used outside of a microcontroller. Consider the problem that we have a decoupling capacitor. Even if this is 100 nanofarad capacitor, decoupling gets some power supply input, and then power supply pin. And then if we switch off the power supply, then the capacitor will discharge itself because of the parasite resistance. Will self-discharge after some time, and then when we try to wake up the microcontroller, the voltage at this point will not rise very quickly, but of course will rise depending on the capacitor value and on the serial resistance, which of course would cost us some milliseconds time wasted for this operation. Therefore, normally in case of idle and standby modes, only CPU and other clocks are switched off, and the power supply is kept. Only in the deep backup mode we have the power supplies part of the microcontrollers switched off. In case of standby, we've got the CPU off, and then one by one clocks being off. Only memory clock and memory power is supplying, because in case of memory, this is static memory, so it does not to be constantly clocked. What is important is the power supply, and the power supply in case of the standby mode is still supplied. Some microcontrollers are having the low voltage regulator, so the power supply, because it's not it's lower, because in this mode the clocks are mostly off, so the power supply required for certain power domains is lower. Therefore, in some microcontrollers we've got also the the regulators are switched to a lower power yet lower throughput regulators, so the LPV rec that is here on the slide. The question is power gating sometimes used for some parts of the PCB device? Yes, of course, that's the problem, but we'll talk about the supporting circuitry in a moment. So I will answer to your question in a few minutes, because of course that's also has to be considered during this design. In the backup mode, no RAM retention. I meant about it, and the problem with backup mode. So this is really the most lowest power mode, because every clock is switched off. Almost every clock is switched off, and almost every power supply block, power domain is switched off, which means that we'll really get down with the values of the power supply voltage here. The problem is, unfortunately, here, and this is very important, and then it's the to wake it up from this backup mode, we need actually to reset everything. It's in almost all microcontrollers, I know, it is required a restart of the software, which means that the software has to be written in a way to reduce the initialization, because then this is a clear power loss, this initialization. So the backup must be used with caution, really, because it may be, if not used properly, the backup mode, or too frequently, then we may really get higher power consumption because of the very long wake up time. In fact, comparing to the standby mode described a moment ago. Of course, in various microcontrollers, those modes may be named differently a bit. So those four major categories, they have different names in different microcontrollers. Here is an example from MSP 430, where there is an active mode which is still active, but then we don't have idle, standby, and shutdown or backup mode. We have here the LPMs, for example. So for example, LPM 0, we have just CPU in shutdown, all the others is not, which means that this is same like idle. Idle, this is backup, because this is backup because we have no RAM retention. No, not here. We have no RAM retention, but also to backup we have this power supply. The rest is in our terminology the standby, the modes LPM 1, 2, 3, and 4. But again, the categories match, just the details are different a bit. The naming convention. Here is an example why the problem may be. So was the was the wake up time, and why we don't switch everything off completely, because this is the off. So the idle, standby, and backup for some microcontroller. I found such a calculations. In case of the wake up time from idle, it's usually instantaneous. So here is 1.2 microsecond, but that's the time required for the oscillator to start. So we talked about internal RC oscillators. So if there is a necessary to start an oscillator, then we need the time. We need to wait for the oscillator to become stable. For internal RC oscillators, it's really about 1 microsecond on this kind of values. Of course, using PLL here would mean much longer time, but we consider here. But PLL and low power circuitry it doesn't match really. So if you have a PLL in microcontroller, don't count on, don't try to switch it on and off. It would do really much more harm than good. But if we, but going back, if we have internal RC oscillator and we switch it off and switch it back again, then this is 1 microsecond. But if we don't have, if we have the oscillator running because we use it for something else, then here the return from sleep mode idle to back to operation is really 0, because it's about switching back the clock. So it's maybe not completely 0, but we talk here about maybe tens of nanoseconds, not much. In case of standby, it really depends on the peripherals. It can be anything from single microseconds to tens of microseconds. Backup is much worse, so it's optimistically estimating it's 90 microseconds, but this is without a large capacitors connected to microcontrollers. And actually those large capacitors that need to be recharged, they make this wake up time from the off state so large. So if we decide, for example, that we have a situations with embedded system, so that we have the embedded system, and we decide to switch off the power completely of the embedded systems, this is really the off mode. So this is really the off mode. Then the problem with the off mode is that we need to really recharge all the capacitors that are here, which is which requires a lot of time, and that's why those millisecond time, of course, this is just to give you an example, it will vary very much on the particular architecture and a particular PCB, even PCB design, but still this is the scale. So this table is to show you the differences, the scale between the wake up time between different modes, because in reality this is true. In reality this is true. Details may differ. And then also an example from something larger, together with the values. This is an example from 32-bit microcontroller. This time again a bit different names and a bit different values. So what to expect here? So the dynamic mode, it is not active, but it is called dynamic mode. And dynamic mode, for example, 3 tapes of microcontrollers, medium size they are, so 401, 405, and 427. So medium size microcontrollers. Medium here means 60 MIPS, more or less 60 megahertz. It's about 100 MIPS. This microcontroller, this is about 200. This is about 250 millions for dry stone MIPS. So it's because it's 32-bit microcontroller. They have the power consumption here not 2, 3, 4 milliamps, unfortunately, but closer to 40 milliamps, so about 100 milliwatts. So already quite substantial value comparing especially to the analyzed a moment before 8-bit microcontroller. So the 32-bit, unfortunately, not that effective. The stop mode here instead of idle, and standby mode, and battery VBAT mode here. So in case of the most the lowest power mode, the lowest power backup mode here. But take a look about the value. So when we switch everything, despite the active current being as high as almost 50 milliamps, in the backup we talk about less than 1 microamp, but it's very close to power off. So from the standby, this microcontroller, for example, requires 300 microamps to wake up, and from this mode we need to reset everything, because that's why the wake up time may really go within even millisecond. So quite a lot of difference. Details vary between architectures. In some microcontrollers we need to laboriously measure it and test in real circuits. In some cases, in some microcontroller families, for example, in this family, we can take the Cube software, the software that is delivered by the manufacturer, and there is a simulator. In this simulator, we can play with the peripherals, we can play with the clocking, and then we can read those values if we get for example 100 200 120 microns or 290, because it depends really on the peripherals that we have switched off and we need to switch back again. So the sleeping modes, they vary a bit between microcontrollers, but the general rule is the same. 4 major ones: so active, idle, standby, and backup 4 types of switching mode. Of course, the question on chat was about the hardware around the microcontroller, and unfortunately, it adds up to the complexity of the whole design. So usually today, you got in your project, in the electronic world today, the microcontroller is the major element of the core, and with the amount of analog and digital circuitry limited to minimum. Yet, unfortunately, there is, even if the amount of circuitry around the microcontroller is limited to minimal, it's usually still existing, which means that in our energy budget, we need to consider this analog circuitry around us, around our microcontroller. In case of this hardware around, there are a couple of rules to follow that you have here on the slide. We'll skip it, so it's not so important for you at this moment, and we really don't have time to analyze everything so profoundly. If you're more interested, we can do it next semester, and of course we can talk privately for those of you that would like to get more information on the subject. Just a few hands, here from practical point of view. So the major things, again, not going into too much details. First, very important, in fact, and very major element when designing a hardware around the microcontroller is the fact of the capacitors leaking. So the capacitors leakage. The value of the leakage really depends on the technology of the capacitor, and if in normal circuitry we don't care about the leakage, because we've got enough. We talk about microwatts here, the leakage itself. So the microwatts, something we are not really interested in. Microwatts, because for example, for electrolytic, 10 microfarads electrolytic supplied at 5 volts means that we have 25 microwatts power loss in that capacitor. So normally we don't care about 25 microwatts. But if we want to supply everything from a coin battery, then those 25 microwatts means reducing the operating time of our device from months to hours. That may happen, that may be so. Therefore, in case of low power hardware design, be extremely careful when using electrolytic and or tantalum capacitors. In general, we shouldn't be using them at all. We are in fact limited just to ceramic capacitors, because the film capacitors are very large, and they are the capacitors from the ancient times, in fact, in electronics. So today, in electronics, in electrical engineering, maybe, but not in electronics today, the only choice we have, in fact, are ceramic capacitors, which deliver us tens of nanoamps. So at the same examples, we multiply by 5, we have 0.1 microwatt. still some values. Still take a look. It's not for free, and that also means that if you want to reduce, if you want your device to really live for a very, very long time, then you should try to design everything with as small number of capacitors as possible. I mentioned some time ago that without thinking, we should be using decoupling capacitors at every pin, at every power supply pin of every digital and or analog integrated circuit. Yes, this was of course the simplification, because if we talk about low power hardware design, yes, we should do some thinking, and then we should choose which ceramic capacitor is really necessary, and which one we can get rid of, because each of them is delivering us some unnecessary leakage. And second important thing is powering external circuits in case of embedded system. Here, of course, we can have it during your projects. You did need to supply the electronic, the analog electronic and digital electronic, and usually you are using an architecture like this one, that we did have a powering circuit, two powering circuits, one power circuit for microcontroller, and second powering circuit for example, op-amps. So that was usually and or sensors, for example, some sensor. So that was usually your architecture. That was usually your architecture. This has a disadvantage that even if a microcontroller goes to sleep, so even if we switch it down to backup state, where it consumes almost nothing, still we've got those elements running. Then we have to, we have three methods now to solve this issue. Method number one, two methods actually, maybe that's simplified. Two main methods. Method number one, which is stated here as 2, we should drive the microcontroller. We should drive this power supply, so the power supply circuitry from a microcontroller, which means that the microcontroller should be able to control and switch off the power supply physically to the analog circuitry. This can be done here. I mentioned about the PMOS transistor, because the PMOS is an element that can be used for this purpose. But today, fortunately, we've got outside, we've got linear regulators with on-off pin, and this is especially for the sake of connecting a microcontroller, and for driving this linear regulator, and for putting it down to sleep, for switching off the power supply for all the supplied circuitry. So PMOS transistor, of course, can be used, but PMOS transistor requires a few components, while in case of the regulator, usually there is just an on-off pin, which we need just to connect to a microcontroller. And then before microcontroller goes to sleep, then this pin is driven low, high, whatever is its state, switching off the whole power domain supplied. Second solution here shown as first one is powering external devices directly from an MCU pin. To be honest, in many situations, this is preferable solution, which means that we have a microcontroller, and then we supply some circuit directly from a microcontroller. What's the positive and negative side of this solution? Positive side of this solution of powering directly pin from a microcontroller is that it's absolutely not a problem to switch off the the elements, so the devices physically, because then we just, in a microcontroller, we just simply change the state of the port from output high to input, from output high to input high impedance, which will of course switch off the power and discharge the power from the from the device that is supplied from this one. Yet this is the advantage, so the full control of the operation. Yet naturally it does have some disadvantages. So the first disadvantage is that we occupy the ports. Okay, if we take larger MCU, that's not a problem anymore. But second is worse even. We've got the limitation of the current which we can drain, which we can draw from the microcontroller. The current, which is usually limited, and then to wake you up. What are the values? We talked about it already. What to expect here? So what's the supply current that we can safely drain from microcontroller pin? Does anybody remember what's the value that you can drain? What's the current that you can drain from a microcontroller pin safely? Usually. Anybody? Any idea? No idea. You're sleeping or what? Usually we talk about 10 to 20 milliamps. Sometimes we can drain more, sometimes we can drain 50, sometimes even 100 milliamps, but it's much more rare, which means that this is really a strict limitation, because 100 milliamps is only from time to time. Usually we have just 10 to 20 milliamps. So this is a serious problem, in fact, and to make everything worse, usually we have here a limitation of the major supply current to something like 100 milliamps. Usually this is a limitation given by the manufacturer of the common power supply current, which of course means that when we connect more than one device here to more than one pin, even if any pin will not exceed 20 milliamps, the current consumption, the current flow, then connecting more than 5 devices, we will be able to go beyond this 100 milliamp limit. So the solution number 2, although cleaner, simpler, faster, has certain drawbacks or deal breakers, in other words. Therefore, in majority of cases, this is the solution 1 that we should follow. So we should supply the circuitry around the microcontroller directly, although through some either PMOS or regulator, which can be switched off when not necessary. So usually we have, so this is the remark number 2. And the last remark I would like to give you about low power design and the circuitry around is the remark about the regulators, in fact, because again, I mentioned it a couple of times, but I don't know if everybody understood it. In case of battery operated devices, every power loss is harmful. I was talking about the leakage current, about the leakage of the capacitors being a few microamps or a few microwatts, and I was trying to prove it that it was difficult. It is harmful, those a few microwatts. But if this was harmful, then what would you say about the situations again met in many projects of you during this semester, that you have, for example, 7.2 volts here, and you've got 2.5 volts here, and then you use a linear regulator, or some of you wanted to use a Zener diode for this one, this kind of circuit. In case of linear regulators, of course, the voltage, there will be a huge voltage drop on the linear regulator. So 7.2 minus 2.5, which is 4.7 volts. If you multiply it by this 100 milliamps current, it gives you about half a watt power loss. Not 25 microwatts that a capacitor has, but half a watt, which is simply lost, simply dissipated here on the linear regulators. So generally, in case of low power circuit, there should be no regulator at all. If you need a regulator, in your design, then we never use the linear regulators. Only switching regulators should be used. Here. So this is the feature. This is pretty important. In fact, this is pretty important from practical point of view to avoid unnecessary power loss in microcontrollers in the design. And of course, and again, don't use Zener diodes. Don't use Zener diodes. Again, why not a Zener diode? Again, a reminder: Zener diode to work requires a certain current to be flowing here, constant current. So the current flowing through diodes, so the Zener current, must be usually above 3 milliamps. So the value should give you an idea why. Why not? So first of all, we need the Zener diode. There must be a constant current flowing. Second of all, the problem is naturally that we need the serial resistor, and there is a lot of current loss, power loss on the serial resistor. So only for those two problems, the Zener diodes must be avoided here. Really must in the design. So most important hints from me about the design of circuitry around a microcontroller. Okay, any questions maybe to this part? Anything unclear? Anything that you would like me to?
I have one question, but not really related to the lecture.
Yes.
So I was thinking about how to connect Wi-Fi to microcontroller, and when you want to use Ethernet, there are some interfaces for that, like media independent something. But there is nothing like that for Wi-Fi, I think.
Because Wi-Fi, in case of Wi-Fi, there is necessary that there is a radio, because in Wi-Fi, when you talk about the let me draw something. Share a presentation so that I have a space to draw it. Okay. In case of Ethernet, the situation is that we've got a microcontroller that's communicated over this MII, so a version of the MII with the Ethernet PHY interface. And the Ethernet PHY interface then uses the cable. That's the structure of the Ethernet. In case of Wi-Fi, we've got the antenna. We've got the radio path of the antenna, and then we've got the transceiver. That's translating the signal to and from the antenna to a digital signal that is available over certain bus. Some time ago, so this is the Wi-Fi. Some time ago, the transceivers were separate chips, and sometimes in the transceivers there was also included the op-amp or the LNA and power amplifier, so the PA and LNA. Just the antenna needed to be added at the outside. Sometimes the duplexers as well. But it's about details. But there was a dedicated interface for this. Today, to be honest, usually we have simpler version. So the transceiver is usually a part of and all this is the part of the microcontroller, and the transceiver, the access to the transceiver is because of the registers. So we've got the registers, and the everything is really integrated, so we don't have any MII here. Yet the Wi-Fi is pretty complex. Therefore, the microcontroller that can handle it is usually not a small one, but the CPU itself is a 32-bit one. And a 32-bit one with a dedicated core, a dedicated software, which is not for free. So it's a software which is delivered by the manufacturers of this kind of chip, because the software the stack itself is not delivered usually. Wi-Fi stack is usually not delivered for free. Therefore, on the market, we don't do Wi-Fi by ourselves, but on the market we buy the ready chip, the ready microcontroller, sometimes with antenna, sometimes with power supply, and the microcontroller is connectable to us by either UART or USB or SPI. So these are usually the interfaces that we have a choice, and the interfaces that we can connect to our microcontroller. So this time not MII, but usually either of those interfaces. So either USB, SPI, or UART. That's the situations with Wi-Fi today.
And is it possible to have, can I annotate this? Okay, so is it would be possible to have on this microcontroller networking stack and send through this interface layer 2 frames to be sent to the...
So usually those microcontrollers, so those here in this microcontroller, I mean, usually we've got IP. At least version 4, but today it's normally that there is a there is the IP and there is a TCP UDP. This is standard UDP, which means that sometimes even, but that's from my experience, it depends. You've got also higher layers like HTTP, or even FTP, although this is not complete standard, but you have HTTP is pretty popular, but TCP UDP is standard. If you have TCP UDP, then it's a very good starting point to implement the high level protocols on your own. It does mean, for example, if you have a HTTP, that you are just sending datagrams and receiving datagrams through the SPI, for example. So that on the SPI you have datagrams, or over UART you are sending data. You are able to send datagrams, so you don't think about the Wi-Fi channels, the configuration on the physical layer. You just send requests, get, post, or whatever you want to send, or you can make a server, for example. Sometimes there is a support for the server and for the client as well. So it really depends on the price you pay and on the manufacturer that you buy from. But usually it's pretty ready for operation, for the usage.
Okay, but working at this level of TCP and HTTP, we give up control over like what is the IP address, right?
Of course, you must have you must add the address during configuration, because if you send a request of a HTTP request and you put there the address, you put the address. The problem, with the TCP IP stack implementation, because the TCP IP stack and the protocols above the TCP IP are in fact pretty complex. So over the years, they got pretty heavy with all those RFCs, RFC documents. They got pretty heavy, and of course you can try to implement by your own. So this is always possible, so that you just prepare Wi-Fi frames. And then you make the fragmentation and defragmentation by your own. Yet from my experience, it's really very time consuming. and it's much better to waste your time on something else, to spend your time on something else, and not to waste your time on the re-implementation of the TCP layer, for example, again, or IP layer, and again and again. And so therefore it's better to take those layers here already, if they are there. So to take an MCU of those layers here, it's because again, you should come to me and we can talk. I can tell you in greater details during consultations, because for example, you have something like lightweight IP, which you can implement in microcontroller and then use just the physical layer from the Wi-Fi modules instead of using ready TCP IP or FTP, for example, protocol. But from practical point of view, this is a better solution to use a dedicated module with TCP IP already there and just to send datagrams than to do everything on a small microcontroller and to waste a lot of resources that are required by the fragmentation, especially in a microcontroller. Mind that HTTP can be 65 kilobytes, can be as long. In microcontrollers, usually we have 64 kilobytes of RAM. So processing of HTTP is really requiring on microcontroller. So therefore, it's better, in my opinion, it's better to take a ready module with just a simple SPI or UART interface and just deliver data and analyze the data, not playing with the fragmentation and defragmentation and encapsulation of protocols. That's my opinion.
So to offload as much of processing.
Yes, exactly. To offload as much processing as possible.
Okay. Thank you.
Thank you, Dan. Any more questions, maybe? If no, yeah. Yes.
I wanted to ask something after everybody leaves, please.
Could you repeat?
I have a question after everybody leaves.
Oh, okay. Okay, no problem. So please don't disconnect then. Okay. Anybody? Any more question? If no, thank you very much. Thank you very much and see you next time. Okay. What's your question?
Yes, sir.
Yeah. Hello, hello. Can you hear me?
There are still some people, because it's quite personal, so that's why.
Okay, let me switch them. Ah.